Hello everyone. Let's discuss another Leetcode problem, and this is also a blind 75 problem. So this is problem number 572, and the title of the problem is subtree of another tree. So probably from the title of the problem, you can make some guesses. So basically, you're given two trees, and you have to check if one of the trees is a subtree of the other tree. So you are given through two tree nodes P and Q, and if Q is a subtree of P, then you have to return true, otherwise you have to return false. So in the example one, you see that this is the first tree with root 3, right? And the red circled one, this one actually matches with the subtree that is given here. So this is the subtree, and this is an exact match with this. So this is, in this case, our solutions should say true, right? In the second case, you see that the subtree looks like 4, 1, and 2. So it looks like this. This is the second tree, not the subtree, sorry, second tree. Now in the first tree, there is something like this, but this is not the subtree. If I start the subtree from 4, this is the subtree, right? Because the subtree has, anywhere you start the subtree, it goes till the leaf. So there is no match here. Okay, although it looks like it just gives you a wrong impression that this part is same with this, right? But the problem is this part is not a subtree. So if I start a subtree, then it will go all the way here, right? And then that's a mismatch. Okay, so to solve this problem, please pause your video and think for a while. But I suggest, if you haven't watched problem number 100, that is same tree, please do that. Like you should obviously watch that first, and that will be actually really helpful in solving this problem as well. Okay, so coming back, let's think, like, let's share my thoughts about how to solve this problem. So my thoughts are like, uh, yeah, already if we know a same tree problem, so it's like using the same tree algorithm. So same tree algorithm, what it did is it took two nodes P and Q and checked if the trees that it starts from root P and Q are the same, right? So can we say that, let's say I just take this subtree, right? So this is P and this is the second input. So if I had just called the same tree check on P and Q, right? It would have said like true, right? Or let's think like this. If I had done the same tree thing on this and this, right? So it would have been, let's suppose this one is P, this is Q, right? So if I had done the same tree on P and Q, it would have returned false, right? Okay. So we understand that same tree algorithm is going to help us here. So what we can do is we can just start from the root. Say we start from the root. So we check if the tree that starts here and the tree that starts here are the same. So in that case, we have to call, say, same tree again, say P and Q. P is here, Q is here, right? And then obviously they are not going to match or something. So that is false. Okay. So that will return me false. But what I do again is if that is false, then I go further. So I will think, okay, why don't I just check with this again as this? So basically, can I check if same tree algorithm works with, say, p dot right and q, right? This was q and this was p, right? So now I'm checking, so what is the tree that starts from, what is the subtree here? This is the subtree here, right? Obviously, this doesn't match with, this tree, right? It doesn't match, so it's false again. And then we can again call, say, same tree, p dot left and q. So what is the p dot left? So this is p dot left, right? So the subtree is going to be this circled one, big circle one, and the this is q. Right now, this is going to give us true, right? So basically, the idea is we will traverse through this tree, the original tree, and after going to each node, we will try to see, okay, after when I'm here, I will try to see if the tree that starts here does match with this the other tree. If it doesn't, then I will just go to my child again, and then I will check if this matches with this. So I will keep on doing it until I don't find a match. Otherwise, like if finally I don't find any match, then no, we can say that this tree is not the subtree of the other tree, right? Similarly, in the second example, first I will check if the tree that starts with root 3 match with this tree. If it doesn't, then I will try again. If the trees or subtree that starts here, does it match with this? Well, still it won't, right? Because the subtree here is this. Then I will try between this and this. I will try between this, the subtree that starts here. This is the subtree with this. No, doesn't work. I will try this with, so the subtree is going to be this, right? With this, it doesn't work. Okay, so I think you understood the problem. Now let's try to code it. Okay, so we write this. I already have coded it. I'm just going to explain it to it. We are going to write this procedure same tree, which is exactly the same problem with problem 100. And we are going to use this function in solving our problem. So basically, if for the same tree, if given two roots, if both of the nodes are null, then obviously they're the same. If one of them are null or the value don't match, then they are not the same, we return false. Or if the value matches, we are not done yet. We have to call this same tree string again on the left child and also matching right child, and until, so you have to check every node by node if the value matches. Otherwise, if the value don't match, I think okay, this is probably not right. Okay, so okay, so this is the same tree procedure now. And what is the complexity for this? Like for the same tree, we have to at least check how many nodes. We have to check these many nodes, right? So these 3 nodes has to be somewhere here, right? So each same tree procedure actually checks the number of nodes that is in the like second tree. So in the second tree, if there are like say order of m, if there are like m nodes here, say m nodes here, so we can say the same tree algorithm is of order of m. Okay, and let's say the original tree has n nodes. Now let's go back to our code again. So we have defined this same tree procedure. Now, now we'll check if this second tree is a subtree of the first tree. Now, first, a few edge cases. This is very important. Say if this second tree is null, right? This is still a tree. So any tree here that is null is a subtree of the original tree, right? Regardless of how the original tree looks like, whether whether itself is a null or nothing else. Okay, so can we check this? So we say if the second tree is null, then obviously I can say the second tree is a subtree of the first tree. Then I will check if the first tree is null. So here is the thing. If the first tree is null, then I return false. Here is the reason. This order is very important. Very carefully notice this. The second tree is null. That means the second tree is a subtree of the first tree. The first tree might be null or anything else, right? If it's null, even if the first tree is null, we don't go to the second line. We are already done here because the second tree is null. We're done. Whether the first tree is null or the first tree has anything, we don't have to worry about that. Second tree is null. That means the second tree is a subtree of the first tree. Okay. But if I reach this line, this second line, it means that the second tree is not null. That's why I'm here, right? In that case, the first tree, if the first tree is null, if this first tree is null and the second tree is, or the first tree is empty and the second tree has something in it, then obviously it can never be a subtree, right? So this one has like 3 nodes, but the first tree is empty. So we can never say that the second tree is a subtree of the first tree. So this is false. So this is very important, just keeping this order. Else if none of those are the cases, that means none of those are null. So we check a same tree. We call this same tree procedure, right? Between the first tree and the second tree. And if this returns true, then we can say, okay, the second tree is a subtree of the first tree. Even if it's same tree, it's a subtree, right? Okay. But if this thing doesn't happen, like this one, the first tree and the second tree are not the same. Now what I have to do is I have to call the same tree procedure again with the left child. So I take the left child of the first tree, or left subtree. I should say the left subtree of the first tree and the second subtree and the second tree, and I will check if they are the same, or if the right subtree of the first tree and the second tree are the same. If any of them are true, then I'm fine, right? This one becomes a subtree of this whole thing. So you may say, okay, the next time even it fails. Okay, it goes under. It again checks with another subtree. And so basically, this time I call this same function is subtree. You see that, right? Very carefully notice that. This time I am not actually checking. So basically I'm starting it all over again. So first I checked, okay, are you a subtree? Okay, so it started here. So how did I do that? So I also asked, like, if you are the same tree, then we're the subtree, right? That's fine. So I check this. This one didn't fail. So what I am going to do is, now I am going to start here and ask here, are you a subtree? Again, the same thing. Are you a subtree? Okay. And this one will call the same tree thing. And if that is not the case, then I will go here and then ask here again, are you a subtree? Okay. Okay, so if this part doesn't give me any result, I'm going to call is subtree function. This is the is subtree function again for the left subtree of the first tree and the right subtree of the first tree. Okay, so now let's talk about the complexity of this algorithm. So as you see, the same tree algorithm is order of m, right? And we call this same tree thing. How many times we can call this same tree thing? Let's say we initially tried to call is subtree on the root, right? If that didn't happen, then I again call is subtree call on this left child. I call is subtree on the right child. So maybe I will be calling this is subtree function on each of the nodes. So basically, how many nodes are there in the original tree? There are n nodes, right? And each of these calls is going to do a same tree check. And that is order of m, right? So that means how many times this same tree call might happen? It may happen, so the subtree call, this one may be called n times, one time for each node, right? This with this, and then this with this, right? This with this. Okay, so n times, and each of these calls is same tree once, and is same tree once. So that means total number of n times is same tree will be called, right? Can we say that? So that means n into is same trees thing complexity is order of m. So it's order of n into m. So that is the time complexity of is subtree. Okay. Now let's talk about the space complexity. Okay, there is a lot of things to erase here. So for the space complexity, notice this. Is subtree calls is subtree recursively, right? It will call recursively, so it may go down until, so suppose if something is like this. So if the tree looks like this, if it's like a imbalanced linear kind of tree, right? Only have to write child. So is subtree, we'll call is subtree again is subtree, again this, right? So the call stack is going to be n of these is subtree calls, right? So this is the call stack. So there'll be like n of these calls, right? Okay, so each of these calls, let's say I'm here, I'm already here. So inside each of these calls is same tree, right? Each of these subtree calls is same tree. So you see same tree. And is same tree is also a recursive call, right? You see is same tree also calls another is same tree. So how many times it may call? Number of nodes, right? So it will have its own call stack, which is like of size m. Okay. So at this particular moment, you see the call stack is taking order of n plus m. Okay. Now the thing is, once I am done here, I go back here. And now already this is like cleaned up the is same tree call stack. So is same tree is again called here. Inside here is same tree is called again. And this again may fill up to m. So in the worst case, it will never be order of n plus m. Okay. Because this call stack is either happening here, is then cleaning up, then happening here, may go to m, but cleaning up, and then it's happening here. Okay. So in total, it's like n order of n plus m. This is the space complexity. Okay, so that is it. And if you have any confusions and other things, what you can do is obviously create an account in Leetcode, go to the solutions and try to just sort based on the votes. And this will actually give you solutions in different languages. And also there are a lot of discussions here. So you can read the discussions, and obviously whatever question you may have will be answered here. Okay. But before going to the discussion of the things, try to solve the problem, or at least attempt to solve the problem. In that case, it will be much easier for you to understand the discussion. So that's it for today. We'll come back with another problem. Till then, goodbye.